Hello. Here we're going to talk about the fundamental theorem of calculus, part 1. So right here in this red box, this is my fundamental theorem of calculus, right? And so let's talk about what this means. When we're looking at this, we've got if f is a function, which is continuous, which is pretty standard, most rules say that. So if the function is continuous on a to b is a closed interval with finite endpoints, then capital F, the antiderivative, equals the derivative of the integral from some constant a to f, to have that upper bound x of f of t dt is continuous from that lower bound a to some b, and we are differentiable on the open interval inside the interval, and its derivative is f of x. So what does that mean, right? F prime, capital F, is the antiderivative of the derivative. The antiderivative of the derivative of the function. This says the derivative of the integral, right? And so what does that simplify to? It simplifies to the original function. Now there's two important points to consider here when we're looking at this. The lower bound a must be constant, and then you'll notice that my function here is in terms of t. The upper bound x is going to plug in for t. All right, so essentially all this says is that the derivative of the antiderivative represents the function. And again, a, the lower bound, is constant. The upper bound needs to be a variable, and that variable could change, but the upper bound is a variable, the lower bound is a function. And really all we're saying is the derivative of the antiderivative, capital F, derivative prime, the derivative of the antiderivative represents the original function. So let's look at what we have here. I'm going to go in and erase some of that because there's a whole lot of business going on there. When we look at what we have down here, this function, we're going to use the fundamental theorem of calculus to determine what? We need to determine the derivative, dy over dx. So, does this integral symbol that we are given, does this look exactly like what we have up above? And the answer is no. What is missing? Well, one, we don't have the derivative notation in front. So we're going to need to add that. And then the other thing we want to think about is those bounds aren't exactly the same because, as we said, x has to be the upper bound. Okay? So let's think about how can I turn this into what we have. Well, one thing to consider is if I reverse my bounds, I can then write that as y equals negative the integral from 5 to x. So I can negate the integral and I can get that constant down on the bottom. And then my integrand is 3t sine of t dt. All right. I also need that d dx notation. I need it right here. And I can't just apply the derivative to one side of the equation, but I can apply the derivative to both sides of the equation. So I have d dx of y equals negative, that's a constant multiple, I'll pull that in front, d dx of the integral from 5 to x of 3t times the sine of t dt. All right, so now it looks like what I need in order to interpret this correctly. All right, so let's go back up there and think about what is happening. What is this notation, which is what I have created right here? What does it turn into? It turns into the function with x plugged into it. So it turns into, go away. It turns into a function of x. So applying that fundamental theorem of calculus, I end up with negative, the negative is still in front, and then I have 3x sine of x. And that's all you have to do. You just have to make sure that it is in the form you want it so that you can apply that fundamental theorem correctly. And so this would be my answer. This is equal. What is the term on the left side? Well, the derivative with respect to x of y is dy dx. So that's my final answer. That is how I use part 1 of the fundamental theorem of calculus.